Hello friends, in this video I'd like to solve the following problem from the German Federal Mathematical Competition, first round 1997/1998. Problem number 4. We wish to prove that n plus the floor of square root of 2 plus 1 to the power of n, this number is odd for every non-negative integer n. So here are my hints for this problem. This problem is rather interesting, I'd say. First, as it is all very often the case when dealing with floor and square root of something plus something, we will consider sequence 1 plus square root of 2 to the power of n plus 1 minus square root of 2 to the power of n. Consider this sequence and try to find a recursion for this sequence, and conclude that every term of this sequence with this new introduced term is a positive integer. And then notice that this term which we have introduced, it's a very small number between -1 and 1. And notice that if n is odd, then this number is between -1 and 0. And if n is even, but not 0, then this number is between 0 and 1. And then notice that our floor can be is connected to the sequence by these conditions. And try to conclude that, well, every term of our sequence must be every expression which we consider must be odd. So give this problem a try. All right. So as I said, let's consider an to be equal 1 plus square root of 2 to the power of n plus 1 minus square root of 2 to the power of n for any natural number. I will try to form a recursion. Notice that what is a0? a0 is 1 plus 1, so it's 2. What is a1? a1 is 1 plus square root of 2 plus 1 minus square root of 2, it's also 2. Alright, and finally, what is an? Now, the fun part begins. Notice that we can write 1 plus square root of 2 to the power of n as 1 plus square root of 2 squared plus 1 plus square root of 2 to the power n minus 2 plus 1 minus square root of 2 to the power 2, 1 minus square root of 2 to the power n minus 2. Alright, so we can write 3 plus 2 square root of 2, 1 plus square root of 2 to the power n minus 2, plus 3 minus 2 square root of 2, 1 minus square root of 2 to the power n minus 2. And now I will write it in the following way. I will write 1 plus square root of 2 to the power n minus 2 plus 2, 1 plus square root of 2, 1 plus square root of 2 to the power n minus 2, 1 minus square root of 2 to the power n minus 2, and I will write 2, 1 minus square root of 2, 1 minus square root of 2. We'll make it smaller to fit in one line, to the power n minus 2. Alright, and now let's see. Notice that this combined with this is actually an minus 2. And also, this is 2 times 1 plus square root of 2 to the power n minus 1. And here we have 2 times 1 minus square root of 2 to the power n minus 1. So it's actually 2 times an minus 1. Which is good news because this completes our recursion. So we now know that a0 is 2, a1 is 2, and an is an minus 2 plus 2an minus 1 for n greater than or equal to. And now, what do we see? Well, it's very easy to see that every term of our sequence is an integer, and moreover, every term of our sequence is an even integer. Why is that? Well, because of the initial conditions. Since the first two terms are even, the next term is even number plus even number, and so on. So it's a very easy claim to verify. So an is an even integer. For n, for every natural number n, actually. All right. Now, next thing. 1 minus square root of 2 to the power of n. Notice that this number, 1 minus square root of 2 is about minus 1 minus 0.4 to the power of n. This number is between minus 1 and 0 if n is odd and greater than 0. And this number also is between 0 and 1 if n is even but not 0. 2, 4, 6, and so on. Alright, and this means that we can write the following. Floor of 1 plus square root of 2 to the power of n. We can write it in the following way. As an minus 1 minus square root of 2 to the power of n. Alright. And now, an, as we know, is an integer. So it's an plus minus this thing. Alright. And now let's notice that this number is either from 0 to 1 or from minus 1 to 0. And notice that this actually equals... First, let's consider when n is odd. When n is odd, then this number is from 0 to 1, so it's just an, because floor of number from 0 to 1 is 0, so it's an if n is odd. And what happens when n is even? When n is even, then we have an, and then this number, if n is even, this number is between minus 1 and 0. Floor of this number is minus 1. If n is even, but from 2 onwards. Alright. And this allows us now to close our problem, because let's consider 3 cases. So we are considering n plus floor of this. Let's consider first when n equals 0. If n equals 0, then this all equals 0 plus floor of 1, which is 1, if n equals 0. Notice second case, when n is odd. If n is odd, then we can write this as n plus an. If n is odd, 1, 3, 5, 1. And finally, this number, it's n minus 1 plus an if n is even but greater than 0. And notice that in every case our result is odd, because in this case we have odd number plus an even number, so this is odd. Then once again, in this case, n is even, so n minus 1 is odd. Odd number plus an even number is also odd. In every case, our result is odd, so this really closes our problem. And that closes, that closes my solution. So remember this trick: when in an Olympic problem, when you see floor and under the floor is something square root of something plus something, it's very often a good idea to introduce the conjugate of this number. So if we have 1 plus square root of 2, introduce 1 minus square root of 2. And if we add or subtract these two numbers, then we'll get an integer, and this floor can be simplified. And also, the crucial was the observation that this new introduced term is very small, and the floor of a small term is either -1 or 0. So that is really it. So thank you very much for watching. I hope that you've learned something new this time, and I will see you next time. Goodbye.